information already. So it will contain scanned notes of each lecture. However, I should warn you that my handwriting is not great and I don't always use my notes when I lecture. So whatever you find there is whatever you find there. Also, you may not find correspondence between the notes of a given lecture and what I actually do in that lecture. I may do more or less. But anyway, they are the notes which I make. You will also find a link on the same page to the videos which he is making right now. And you will also find the home assignments on the same page as and when they are ready. And you will find a set of links to resources on general relativity on the net, also on that page. I can't remember what else there is on it. Course outline is on it. So please look it up. And also, if there are any sort of changes in schedule, the schedule of the course is there, including the venue which is right now lecture theatre. So please, so today I'm sorry, maybe some of you didn't know where it would be. But from next time, if you have any doubts, just look at the website. That I would update instantly if needed. Okay, good. Are there any questions based on what I did last time? Was that clear? Okay, if you say so. Very good. So we'll continue with what we did last time, which was actually to a little bit skirt around the subject of relativity and talk about curvature from a very physical point of view of a classical particle propagating on a curved space. Actually, I did most of that last time, but there's one little thing extra I want to do, and then I'll turn to my goal, which I sort of told you, which was to try and combine or unify Newton's law of gravitation with special relativity and convince you that with little bit of intuition, but mostly just following logic, we are led to the ideas of general relativity. I actually don't know whether this is how it was done by Einstein, and I haven't found anybody here who has bothered to read Einstein's papers, including myself. Probably a big mistake, but anyway, now that the subject is sort of there, we can approach it in whatever way in modern times you find most logical. Okay, so this is what we studied last time. The Lagrangian for a free particle, free non-relativistic particle on general really is my way of saying curved, but it could be flat as a special case. So any space which is symmetric. And the last time I mentioned to you that the equation of motion of this Lagrangian, obtained by making this stationary in the usual way, came out to be x double dot I plus gamma I j k x dot j equals 0. And I said this has a name, is the geodesic equation. I also defined for you gamma. And one reason I'm doing things this way is that I don't want you to think that these concepts like metric and affine connection have anything particularly to do with general relativity. These are just concepts that arise when we study manifolds. Okay? General relativity involves space-time manifolds, and space-time manifolds are a very novel thing at the time Einstein talked about them. They were not perhaps well known to mathematicians, but ordinary spatial manifolds are quite well known. So we are going to talk about those for a little while, and then we'll come to the really tricky question of space-time manifold. So this is the symbol that appears in this equation, and now I want to know from you how many people have actually worked this out as the equation of motion from that Lagrangian. Okay, how many people have not? Nobody? Okay, good. Very good. I think it's very important that if you want to follow what I'm doing, you have to work these things out. There's no other way. And I'm sure you have all heard that general relativity is a difficult subject. That's a correct statement. But one of the things that looks difficult until you do it is working out these things. It's not difficult. After all, nothing could be really simpler than that. And the Euler-Lagrange equations, surely you know, therefore this can't be difficult, but it can be tedious. And soon, as you practice these things, you will encounter shortcuts and you'll find ways to do these calculations faster. But if you don't do them, then you won't find any way to do them faster, and you'll become scared of them as time goes on. So that's why I strongly recommend that these kind of things will work out. Okay. Now I want to step back from this and ask a question. Here's a nice Lagrangian. What is x? It's the coordinate of the particle. Okay. So what if? Okay. Before that, let's first do an example so that this doesn't look so mysterious. Here's an example. Now, what's the simplest manifold one can sort of think about, which is not just flat space? I think it's fair to say that it would be a sphere, surface of a sphere. So let's consider x1 squared plus x2 squared plus x3 squared equals r squared. This is one equation in 3 variables. So it's what we call the surface of a sphere. Mathematically, this is just called a 2-sphere or a 2-dimensional sphere. Now here I didn't say what values I and j run over, but they can run over any number of dimensions. So we'll take this in this example, we'll think about this where I and j run over only 2 values. Nothing could be simpler than that. But we don't know in principle what's the metric of this 2-sphere. So we are going to find it out just using our very simple ideas of classical mechanics. Okay? Classical mechanics tells us that the unconstrained particle, that is the one which is free to move in all of x1, x2, x3, had a Lagrangian half m x dot squared, which is summed over, where here x dot I summed over 3 values. Okay? And here's a constraint. So how do I find the Lagrangian of the particle which is constrained to move on the surface of this sphere? What should I do?
Use generalized coordinates. You can use generalized coordinates.
Generalized coordinates. Yeah, okay.
Use a Lagrange multiplier.
Yeah, I mean, but actually there's even something, if I could use Lagrange multiplier, there's something even simpler. I just solve the constraint and plug in the solution here. Okay, so here's the solution. The constraint is solved by saying that x3 dot is square root of r squared minus xa. Now I have a slight problem with notation because I have to distinguish one of these from the other two. So here I'm going to say that a runs over the values only 1 and 2. So this equation is obvious, right? It's just the solution of that constraint. Okay, so if this is x dot 3, of course I have to make a choice which of these coordinates I solve for, but it's hardly makes much.
There won't be a dot.
There won't be a dot. I meant to say this. I'm sorry. Thank you. X3 is that indeed. I was about to calculate its dot. So I do this and I plug it in to this Lagrangian. So now the Lagrangian is half m. So first of all there are 2 terms, x dot a, where a goes over that 1 and 2. And the third term is a half m x dot 3 the whole square. Okay, so what is that? That's minus 2 xa dot upon 2 square root of r squared minus. Is that clear? This thing in here is the dot of x3. Because I have a square root, so it comes down with the factor 2, then I differentiate this argument and I get minus 2x, etc. Clear, no? Okay, so that's nice, the 2's cancel. So this can now be written as a half m delta AB plus x a x b 1 r square minus xc. Now, one thing that I would like you all to get used to is that without any warning, I will rename dummy indices wherever there are summed over. XA, XA and XC, XC are exactly the same thing because both of them mean sum from 1 to 3 of that thing. Okay? 1 to 2. Thank you. I'm glad. Please do correct me when I say wrong thing because otherwise it can create confusion. Exactly. In this case, 1 to 2 of that thing. So I will be changing in dummy indices as I go along with no apology at all, and I'd expect you to find that, to get used to that. If you have any queries, feel free always to ask. Okay, this. So now, what name should we give to this object? GAB of x. So we are done. We've just found the metric of a two-sphere using nothing except classical mechanics. Pretty good, I think. Okay, we weren't taught any geometry to do this. We just found a representation of the metric of a two-sphere, which possibly most of you hadn't seen before. It has to be that, right? What else can it be? Because we convinced ourselves that that's the general Lagrangian of a particle on a curved space, and now we found a Lagrangian of that form where there's a particular function of x. It's not a simple function, it has x squared here, so it's highly nonlinear function. If you expand about small x, you'll get all powers. Secondly, you're not always allowed to expand about small x because nobody says this has to be small. But whatever it is, it has to be the metric of the two-sphere, and so here's a concrete example for you. Now this example shows a little bit of a lesson that you will have to also learn over time. So it's a little question you might have. What if xc equals r squared, or in fact more generally, if it's greater than or equal to r squared? Something surely must be wrong with that because the original constraint doesn't allow that, right? The original constraint says that all the three xi's add up to r squared. So individually none of them can be more than r squared, not even any two of them. Because then the point would end up outside that sphere, but the point has to be on the sphere. Okay? In fact, such a thing would correspond to the third guy being negative, being imaginary. The square root, under the square root, you would have something negative. So it's valid. However, if you look at this, okay, we see something going wrong when xc is r squared, but we don't see anything obviously wrong when xc is greater than r squared. Still some function, right? So this is a lesson that when we see a metric, we should keep in our minds that the coordinate may have some limited range beyond which the metric may not make sense, but the metric may not necessarily start screaming at us, oh, it doesn't make sense, just by putting in some illegal values. We may have to do some analysis to find out that this metric doesn't make sense. So now I can tell you, as you would have expected, that this metric does not make sense for xc greater than r squared, but you won't be able to tell it just by looking at this. Okay, you'll have to do something else. Now, in order to do something else, we'll have to talk about curvatures and other concepts involved with curved spacetimes, which I'm leaving for perhaps the next lecture. Yes?
So xc equal to r square corresponds to the sphere example.
No, no, because the c goes over 1 and 2. Okay, so what xc equals r square corresponds to is that x3 is 0. Okay, that's a perfectly legitimate point. Take a sphere. Okay, let's imagine that I cut it with a horizontal plane. X3 is the vertical direction. So the horizontal plane is a circle. That circle is xc equals r squared. So those points are there. In fact, this is interesting. Those points are there on the sphere, but this metric looks bad at those points. Okay. On the contrary, xc greater than r squared are points which are not there on the sphere, but this looks okay at those points. So you see, we learn that when a metric looks bad, it may not be bad, and when a metric doesn't look bad, it may still be bad. This is an important lesson, and it will follow you through the entire course. Okay, so let's write that lesson. So for xc equals r squared, metric looks divergent but is not really so. So part of our job is to understand what this really means. In fact, you can see that if that was the case, we would have been better off eliminating not x3 but one of the others, x1 or x2. Then on these points you wouldn't have run into any trouble. Okay? You see that? So we made a choice of eliminating x3 and we find the metric has some ugly property when that thing which we eliminated is 0. So we learned that okay, if that was the part of the sphere we wanted to consider, we would have better tried to eliminate some other coordinate out of those three. So we learned that coordinates should be chosen at will for our convenience of study. That's one fact. The second fact is that for xc greater than r squared, metric looks okay. I mean not very okay because this term is negative, but whatever it is, as long as it doesn't completely cancel this, it seems reasonably okay, but it's not really so. So these two facts should convince you that we need to learn geometry a bit better. Just doing this stuff is good, but it's not good enough. It points some problems in our understanding of the system, which have to do with choice of coordinates. Okay, I hope it's clear that in some way these have all got to do with coordinates. Okay, because we are taking certain numerical values of certain coordinates and we are finding properties which are a little bit strange. Okay. Now, this motivates us to ask the following question. What if we change from xi to some different coordinates? Now I have to apologize about notation. Now I'm not anymore talking about that exercise. Now I'm talking about a general situation. Okay? The reason I have to apologize is because there I went from 1 to 3 and A went from 1 to 2. But now I'm going back to the general case. So I goes over all the actual coordinates of the space and the Lagrangian is that one. I hope it's okay. I mean I will warn you, but sometimes we have to change our... We are trying to do different things. Here I was trying to understand the sphere as a space embedded in flat space. Okay, but here I am back to a general space. I don't know what space it is, but it has a metric Gij. I don't even know what I and j go over, but some 1, 2, 3 up to some number t. Okay, but now I am asking a different question, which is what if I change from xi to some different coordinates? So it's good to give those different coordinates a name. We call them xi prime. Okay. Now, under the change xi, so the way to do this, okay, it's very confusing to change coordinates because there are two sort of points of view, active and passive. The way I like to do it is to say assume xi are functions of some new coordinates x prime. Okay, so you're working in coordinates xi, which were until now independent. Now I'm going to assume that they are dependent on some new coordinates. Okay, and then by substitution, I can get the Lagrangian in the new coordinates. That surely can't be any hard work. I just put this into that Lagrangian. So what do I find? I find that L is half m Gij of x, which now is given as a function of x prime. Okay, and now I have to write x dot I, but from this, that is dxi, partial derivative xi, x prime k, xj, x prime l, x prime k dot, x prime l dot. Is that clear? So far so good. What did I do for g? I didn't do anything. I just wrote that g is a function of x, which in turn depends on x prime. But for x dots, using chain rule, I replaced x dot I by dxi dx prime k, x prime dot k. and similarly x dot j by dxj dx prime L x dot prime L. That's all I did. Okay? Some panic seems to have settled in on the audience. What's the problem? Until now, people were nodding. Suddenly something has happened. People are nodding. Please interrupt me. We can keep this very informal. I don't have to go rushing through anything. One thing I'm sure that I'm not in any hurry. Everyone okay with this? Okay. If you're okay with this, we now have the opportunity to decide that this whole thing, if we write as G prime AL of X prime, okay, this is the definition of G prime. What does G prime mean? It means the metric in the new coordinate system and evaluated directly as a function of the new coordinates. Okay, if we do that, then the Lagrangian is this, and it has the same form as the original one, but the metric is not the same function as before. That's why there's a prime on G. Putting a prime on the argument tells us that it's evaluated on that argument, but putting a prime on G says that if that was some function, this is not the same function. Why is it not the same function? Because of this thing. This complicated law means whatever was the functional form here, for example, imagine that this was that thing over there in brackets, delta AB plus something something. It's being multiplied by this, so now it's a new kind of function, it's a different function. So we learn that in a different coordinate system, the metric is a different function. Okay. Now, as physicists, or even if we were mathematicians, how seriously should we take it that it's a different function? Does it mean that after changing coordinates, the space is a different space? To make the question very concrete, if I were to change coordinates from those coordinates on the sphere to polar coordinates theta and phi on the sphere, would something happen to the sphere? No. The same sphere in the same place, exactly. Okay? But in terms of theta and phi, I'll show you in a second, I can write the original Lagrangian, this one, GAB x dot A x dot B, but it will look quite different. In particular, the metric will not have that structure, and it even won't have these weird properties. We'll find that we are not able to really get to any place that's not on the sphere. Everything will be properly on the sphere. There are different coordinates. All coordinates have their own peculiarities. Okay? So, this is the key step about changing coordinates. And this teaches us that to maintain the geometric nature of the space, which is to say, the space has a geometry independent of how we describe it. We assign the law, which most of you are taught as a law just because somebody says it. We have actually derived it. G in a new coordinate system is and you surely know the name of this rule. This says that the metric G is a second rank tensor. In some books call it a covariant tensor. This is probably a good notation. Okay? So have you seen why this became necessary? Same particle, different coordinate system. Because of the chain rule, the x dots changed in this way. To keep the Lagrangian form invariant, I need to absorb this in my definition of how the metric changes. Now the metric has a different functional form, But by doing all this, I am assured that whatever this system is, it's actually the same as the old system, okay, with a different functional form for the metric because I'm in some new coordinate system. And now we'll do an example which hopefully will solidify this for you.
Can I ask a question?
Yes.
So you said that in order to keep the form of the Lagrangian invariant, we absorb it in G.
Yes.
But someone could have done the same thing inside the coordinate thing. So is this just a matter of definition?
It is actually. You could have done it otherwise, but at the end of the day, in that case, you wouldn't have found that the Lagrangian describes a particle moving on a space with metric G. You would have had to call it something else. Okay? Our prejudice is that the space doesn't depend on what coordinates I use to describe it, and that's in fact the key property of what's a manifold. A manifold is something defined using coordinates, but which ultimately doesn't depend on the coordinates with which I define it. Okay? And it's very sensible when you think that, maybe the only manifold we'll be talking about for some time, next few days, will be this two-sphere. I can give you a dozen different sensible coordinate systems on it. Okay? But the two-sphere doesn't change each time I change my point of view. Okay? So in order to have that geometric interpretation and think that and to do something that depends on the sphere and not on me, I must have the freedom to change coordinates. Okay? But I can't insist that the metric on the new space is Gij of x prime. That would be wrong. That wouldn't behave like the metric on the new space. However, this thing will behave like a metric on the new space. Good. Okay, and that leaves me with two little things I need to do, and then finally we can stop talking about spaces and start talking about gravitation. First, in fact, the example that I promised you. Now I've run out of words. I just have to go back to the top. So here's an alternative approach to the two-sphere. What I'm going to do is take the same constraint equation, but I'll solve it in a different way, which will give me polar coordinates on the two-sphere. And what I'll do for that is I'll just write that x1 is r cos theta cos phi, x2 is r cos theta sin phi, and x3 is r sin theta. My drawing is not very good, but I think you know what I'm talking about because hopefully you've done it. So I'm here, then I join this, I drop this here, and then this angle is theta, and what is phi? This is x1, so this is phi probably.
So explicitly r sin theta was
No. That depends whether you take theta from 0 to pi or minus pi by 2 to plus pi by 2. I've taken it minus pi by 2 to plus pi by 2. Now it's natural at this stage that you will be remembering formulae from your books and comparing them with my formula and finding that they disagree, which is fine because it shows that you are trying to compare with something. However, one thing I would like you to do is try as far as possible to derive everything from first principles there and then. Here is theta, I've drawn it for you. So this has to be cos theta, that one has to be sin theta. It can't be the other way. For the theta I've drawn. If I had marked theta this way, then they would be reversed. Of course, and both are equally good. Anyway, here we are. I'm saying all this because I find that undergraduate textbooks do all this, but they never tell you where it comes from. They never urge you to derive it yourself, draw the picture and find it out and use. Somehow it seems like it's some kind of law. And at least I never like that way of doing things. So I'll be doing things my way. Now, if you take these and square them and add them, you get small r squared. R is a coordinate, remember. Interchange these three coordinates with these three coordinates. So therefore, constraint is solved in this case by simply setting r equals r. And now we have two coordinates theta and phi. But what's the metric in terms of these two coordinates? That's very easy. Just calculate dx term. Calculate x dot I, x dot I, and you'll find that this comes out to be that this is a long calculation because you have to differentiate this, and each of these derivatives gives you several terms, and then you have to square and add. I'm going to drop already the terms that involve r dot because now we are going to fix r to capital R, so r dots will not be there. And so what you'll finally get is this theta dot square plus cos square theta phi dots. Right. So here we have the Lagrangian in the form GAB x dot A x dot B, where A and B take the values theta and phi instead of 1 and 2. Okay, so now you can see that the metric GAB is, as a matrix, just 1 and cos squared theta. Or maybe it's r squared and r squared cos squared. It's diagonal. Okay, so this is certainly not the same metric as this. At least it's not the same function or anything as this. Okay, and now you see that I'm doing the same thing though. Here I eliminated the constraint one way to get the two-sphere metric. Here I did it another way, but it's the same two-sphere. Okay, this is being studied in three-dimensional coordinates with one constraint. That's why there are really only two coordinates on this sphere. They are, if you like, take a sphere and imagine I parameterize it using x and y coordinates. Because once I give you a point x and y, z is solved by the constraint, by that constraint. So I know what point on the sphere it is. Here on the other hand, I use those angles that I drew there. Transcription between the two is straightforward. But here's the functional form in these coordinates, here's the functional form in these coordinates. And now you can see your exercise. Show that if x prime A, I'm using notation x prime A as the two coordinates theta and phi, then this is really g prime of x prime. Okay. Then g prime AB of x prime is dx. Okay. The tensor transformation law, I'm asking you to check this by converting from coordinates x1, x2 in terms of which that's the metric, to coordinates x prime 1 and x prime 2, which are these, in terms of which this is the metric. So it should be true that this is equal to that contracted with this stuff. Okay. Notice one last amusing point. This metric is diagonal. Its off-diagonal components are 0. This metric is not diagonal. It has off-diagonal components there. So you see, lots of things can change when we change coordinate systems. Okay, I'll keep giving exercises, but then once in a while I'll give you a home assignment sheet which will have the most important exercises there, and you can do them. Good. Are there any questions up to this point?
Sir?
Yes.
When we are talking with x1, x2 and x3,
yes,
and we try to, using the constant, we try to remove one x3,
yes,
then x3 equals to 0 comes up, there is a problem with the metric.
There's an apparent problem.
Apparent problem.
Yes.
If we have tried to remove not x3 but x2,
yes,
then x3 equals to 0 will be the same problem.
Yes, but it's a different point on the sphere. So the logic is that we can study part of the sphere in one set of coordinates and another part in another set of coordinates. And if you pursue this thought, you will reach the definition of a manifold.
Isn't it a projection on a plane when we just remove one constant?
Yes.
So isn't it the projection on a plane actually, and that will for some point it will have some ambiguity.
That's right. I mean, whichever way you read, all these coordinate systems actually have some point where the metric is not well defined. I haven't stressed upon that fact now. It's also true in theta phi coordinates because at the North Pole phi is not well defined. North Pole and South Pole. In fact, it's a theorem. If the manifold is really interesting enough, it can't be covered with just one set of coordinates. So whatever we do, something will be missing. So later we'll understand that whatever the manifold, and even if it can't be covered with one set, as long as we know easily how to go from one set to another set of coordinates, then we can study the manifold as well as we want.
What is the precise definition of a manifold?
Yeah, I'm going to come to that. I'm trying to build up to it. Hopefully you will guess it by the time we reach there. Yeah.
What that constraint does is you have only covered the hemisphere, not the whole sphere.
That is not true because I could have both. I could say that it's plus and minus that. You're right that this constraint, the way I've written it, gives me the hemisphere, but I can also include point x3 equals minus that. So there are two solutions, right? Plus and minus.
But so if we consider this thing,
Yeah.
only the hemisphere, then it's apparent that this thing will
Then
have
it's
a-
apparent that the equator is some kind of boundary and something. But even then, there should be nothing wrong with it. Even if it's the boundary of a hemisphere, why should the metric be singular at the boundary? It's not that the metric becomes singular at the edge of a space. That's not generally true. Yeah.
If you take the other plane and if you substitute for other coordinate, then the equator will be the different circle.
Yeah,
and then
you're
you can see that
different.
it's
That's right. That's correct.
Sir, but I was thinking that if we have three coordinates, x1, x2, x3, orthogonal coordinates, then what happens that which one of these three x2 I want to take it 0 and remove it, that equator corresponding to that x2 is getting some apparent problem in the metric.
Yeah.
Then the sphere is unidirectional, it is invariant under rotation.
Correct.
I could have taken it in
That's
any
correct.
point. That means that any point of the surface is in the metric should be
Correct.
apparently
What
problematic.
no, any point the metric should be
Apparently problematic.
in some coordinate system.
But
Yeah,
in
that's
some other
correct.
coordinate system,
That's
not
also true.
any
If put it another way, if I give you a space and if you want to find a coordinate system which is bad at some point of that space, you'll always find it. That's correct. That's always true. If you want to find a bad coordinate system, it's very easy. If you want to find a good coordinate system, not so easy. But what is important here is not that. What's important is when we have a bad coordinate system, how do we realize that it's only the coordinate system and not the space? And you have just given me a proof for the sphere. You said it can't be possible that the equator of a sphere is a bad place to be because if you take all the equators, you've got the whole sphere. So either the whole sphere is bad or nothing is bad. So it can't be bad. That's correct. That's a proof. That proof will not work if the sphere didn't have rotational invariance. Okay, supposing it was some very, very deformed kind of space, then I can't just say that, okay, every equator is as good as every other. But in this case, you're right. The proof is correct. It shows that there cannot be anything wrong with it.
if we find any of this symmetry which covers entire space,
Yeah.
and union of all those problematic set will cover the whole set,
Yes.
then it will.
Yeah, I agree with your statement. Except, why did you bring in the word symmetry? I think you mean you find many coordinate systems,
Okay.
each of which cover some part of the space, such that with all those coordinate systems we can cover the whole space.
yeah.
Then we are done. Now we are getting closer and closer to definition of a manifold. That's exactly what it is. I'm glad. So basically I agree with everything you all have said. Okay. Now let us now do one little thing which looks like it may not be necessary at this stage but will be very useful in the future, which is this. What if we make an infinitesimal change of coordinate system? So the difference between that and what I did above, what I did earlier, or maybe it was below, was to say that x becomes a function of x prime, but I didn't tell you what function of x prime. Now I'll be saying that x and x prime are equal to each other plus a small amount. Okay, so let's see what this tensor transform. The goal is to see what this tensor transformation law looks like in such a case of infinitesimal change of coordinates, because it's a very useful thing to do. It really is one of my favorite equations, and it's not very. This equation you would have seen a zillion times, but the equation I'm going to get, possibly you have not seen, possibly you have, I don't know. But what we are simply going to assume is that x a is equal to x prime a plus psi a of x, where psi is infinitesimal. Sometimes it's called epsilon. So basically neglect order psi square and higher than that. So just keep first order in psi. Okay. What's the procedure? We take this and we plug it into this equation and we get whatever we get. It's surprisingly subtle, so let's do it. The reason it's subtle is that two things have happened in that equation. First of all, there's a difference between x prime and x, that part is easy. But there's also a difference between the functional form of g prime and the functional form of g. And what this helps us to do is to disentangle those two things and concentrate on the change of functional form. Okay, so what we want to find out delta g AB, which is defined as g AB prime at x minus g AB at x. You see that in this equation everything is at x, nothing is evaluated at x prime. So the difference between this and this is the infinitesimal amount by which the function g changes. Okay, so we take out the change of argument already, and whatever we are left with will give us this. So let's do the calculation.
So
Yes.
the metric g prime
Yes.
is defined in the prime coordinate system.
Yes. But now the prime and unprime coordinates are related by a simple transformation with an infinitesimal parameter. So I use this equation to go back to those. Okay, that's the whole idea. Okay. So let's see how this works. So first of all, on the left side of that equation, we have g prime AB of x prime. So let's do LHS and then we do RHS and we compare. So this is exactly doing what I just told you, is g prime AB at x plus psi. And this just Taylor expand to first order. X prime is x minus psi. Okay, so this is g prime at x minus psi c del c at x. So LHS is done. Okay, now let's do RHS. For the RHS, the first factor is delta A C.
So would it be G prime?
Yes, but it's, yeah, good. Thank you. Won't it be G prime? No, it will be G. Tell me why.
First order. First order.
Very good. This could have been still G prime of x, but there's already a psi, so G prime and G are equal to that approximation.
So what is the notation? Delta C.
Del by del xc. But you better get used to it. It's the notation. Delta subscript I or A or mu or C just means partial derivative with respect to x of that coordinate. I thought I'd used it somewhere. Okay, if I haven't, then this is. Okay, so the RHS of that thing, the first bracket delta xc by delta x prime A is, you don't have to worry about the sign. It's so it's del A psi C. That's the first bracket, right? The second bracket is delta B D plus del B psi D, and then here I have D C D. So you see that all primes have vanished now. Okay? We only have to expand out this, and that too we only have to keep the term delta with g, which is 0th order, and then these two cross terms, which are first order inside, and we drop the term of this with this. So the first term where we keep delta with g is GAD, and then we get delta A psi C G C B. Okay, because the Kronecker delta B D sum with G C D, when I perform the sum over D, it sets this index D to be equal to B. So that's G C D. And then the other term I can just write down by symmetry between A and B. So that. Okay. So as I said, it gets tedious, but there's nothing mysterious about any of this, I hope. Just like taking an equation we are all agreed on and now expanding it to first order, because it will be easier to study the equation in first order.
It should be GCA.
GCA, quite possible. Yeah, indeed, this looked wrong. Thank you. GCA. And of course, G is symmetric, so CA and AC doesn't matter, but the placement of indices is important, and this is correct. So now what do I need to do? Just equate this side and this side, and we see that the first term on both sides, when I subtract one from the other, I'll get what I want, which is delta G. So everything else will tell me delta G. Delta G comes out GAD of X is done something wrong. I'm not getting a sign the way I want it. Let me write what I want. X prime is X minus psi, what have I done? X prime is X minus psi, very good. So maybe my notes are wrong.
So there is a minus sign in the RHS part. It is minus sign.
Really?
Where? No.
No, I don't know. The RHS looks fine. So maybe it's just my notes were wrong. Yeah, I think it's just my notes that were wrong. I think this is plus.
And there should be a side D.
Sorry?
There should be a side D, I think.
Side D.
In the third term.
D.
D.
No,
Where
C is
is
a
D?
contracted.
C is contracted.
C is contracted.
C is the dummy index.
A and B are free units.
Yeah, C is contracted.
C is contracted.
So what is D? I think it's okay. Thus I can see this is okay. So it's okay. If you find out that it's not okay, let me know. But I think this is fine. Good. Okay. So now let's ask the following question, which is, this is the answer actually, so we are done. We wanted to find out the infinitesimal form of tensor transformation law for the metric, and what we found is that the metric gets modified by adding these three things. Okay. Now there are two comments I can make. One is, this is rather a tedious exercise, but it's quite an interesting one, that this can be rewritten as dA psi B plus dB psi A, where dA psi d is defined to be ordinary derivative, ordinary partial derivative minus this. And we've already encountered this gamma symbol before. I've written it down for you earlier. Okay, it's called the Christoffel symbol. And my claim is that with a bit of manipulation, you can rewrite this as this. Now, I'm just terribly nervous about signs, but I think they will work out. Sorry.
Is in your note there is one sign negative?
In my note, this one was negative.
That can't be because A and B are symmetric. If that is negative, then the second term has also has to be negative.
No.
This term is different from
These
the
two
other.
terms are added. This third term can be
Okay.
negative without violating symmetry. But I think my notes are wrong, and I think this is right. Anyway, you'll find out. You'll do the exercise, and this part is easy. This is the simple expansion. This is a non-trivial statement that it sums up into this nice form where capital D is a new kind of derivative called covariant derivative, which we'll reintroduce when we do our formalism. But it's defined just like this, and it uses the good old Christoffel symbol, which had already occurred earlier. Now, just to see how this can possibly be true, of course, capital D A psi d contains this term, which is here. Okay. Oh, sorry, I forgot one more thing. And psi. I never defined psi with its indices down. Psi was always with its indices up. So psi A is defined as the contraction. Sorry, what? Okay, this is very important. So very roughly you can see that, well, contracting psi with g will bring its index down, but of course you can't just do that because there is this derivative here. Okay, so derivative of psi up with g times g is not the same as derivative of psi contracted with g. There's an extra term.
That extra term will bring in the Christoffel.
Exactly. The extra term will bring in the Christoffel symbol. So whatever it is, it's all something you can work out. Okay, and it comes out to be this form. And the last point to be made about this is that suppose to start with GAB, this is a very special case, was equal to delta AB. What do we call a space where GAB is delta AB? We call it flat space. Okay? Because the metric is just the usual metric, diagonal 1, 1, 1, 1, 1, the Cartesian metric. Actually, correct name is flat space in Cartesian coordinates. Because say in polar coordinates, it won't look like this, it's Cartesian coordinates in which it looks like this. Suppose this is the case, and suppose I try to make a coordinate transformation. Okay? Then after the coordinate transformation, GAB will not be delta AB, because it will change by this amount. Okay, but this simplifies a little bit. The change now will be ordinary derivative. Why? Because the extra term are these, but these things all depend on derivatives of the metric. But if I've taken the metric to be delta AB, then all its derivatives vanish. So everything simplifies greatly. The Christoffel symbol vanishes in the original coordinates. And therefore the change in metric is this very beautiful form, del A psi B plus del B psi A. Okay, and here psi with a lower index and upper index also doesn't differ from each other because the metric was delta A. Okay, so this is a rather pretty equation, and I wanted to keep it in your mind because in a very unexpected way it will show up in the next. By the way, how long are my lectures? I haven't even thought about that. But I think 1 hour 15 minutes. Is that right? 1.5 hours? You can do something to me if I don't teach for 1.5 hours. I get very disinclined to go beyond 75 minutes. I should ask them that. Okay, what we'll try to do is keep it like 1 hour 20 minutes or 1 hour 15 minutes, and then if there are some questions, is that okay? So I still have 20 minutes. So either in the next 20 minutes or more likely next time, this equation will pop out in a completely surprising way and it will give us the motivation we need to study general relativity. Okay? So then, I have completed my discussion of, preliminary discussion if you like, of curvature or of particles moving on curved spaces, and now we'll turn to real physics as it were. We'll start thinking about Newton's gravitational theory, and we'll also in parallel study electrostatics a little bit, and we'll try to see why these theories are not relativistic and what can be done to bring them in line with special relativity. And we'll find two different answers for electrostatics and for gravity. So first, any questions on what I've done here?
Flat space, how do we, like if you write it in polar, we will see it's not 1 on 1. So how do we differentiate whether it's flat or
Very good. That's a very good question, and that's again part of the study of curvature. So let me just give you this much information that the metric, of course, encodes, even if it's given to me in one coordinate system, it encodes the properties of the space. But as you say, they can be hidden. For example, the metric is a function of theta and phi, but the space is secretly flat. But I don't know it by looking at the metric. So what question should I ask here? The answer is that there's a quantity called the Riemann curvature tensor. Okay? And the Riemann curvature tensor is more complicated than the metric, but is derived from the metric. It is the second derivative of the metric. The reason it's complicated is only because when you have second derivative of something with two indices, the end result has four indices, and there are many ways to differentiate it into more things, and so there are many terms. But finally it has a geometric meaning, and its geometric meaning is very beautiful. This is what it is. If all components of the Riemann tensor are identically zero in one coordinate system, then they are identically zero in all coordinate systems and the space is flat. Okay? So if I am not sure what's going on with my metric and I'm not able, one thing I can always do is try and guess the coordinate system in which the metric becomes this. Then I'm happy. But if I'm given the metric in some other coordinates and I'm not able to guess the coordinates in which it becomes this, then I always have the freedom to put this thing in my computer and ask it to calculate the Riemann curvature tensor for that metric, and that answer is final. And that answer is independent of coordinate system. If it's zero in one coordinate system, then it's always zero and the space is flat. It's a very beautiful result. And it's the reason why we have to do a little more formalism, because finally the metric is nice, but its second derivatives are more nice. That's what the moral of the story is. More difficult, but also more nice. Okay. So this was fine, but are there any other questions at this level? Yes.
In the discussion we've done so far, we have studied what curvature is, but we haven't yet come to what causes curvature. Right?
You also haven't studied what curvature is. I haven't told you anything about what curvature is. I just told you what a metric is. But as I just was telling him, curvature is not the metric, but the second derivative of the metric. And as you've seen, even the first derivative of the metric is pretty hard. It's all the terms which go into this thing. Okay, the second derivative is harder still, so we haven't done it actually. So in a sense, I've asked you to accept on faith that something can be curved without giving you a proper definition. Nevertheless, you had a question. What was the question after that?
That was it.
That we've been doing curvature, but something you said we haven't done.
We haven't yet done what causes curvature.
Causes curvature, certainly. In fact, there's no possibility to ask what causes curvature, because the problem I'm studying is of a particle constraint to move on a curved space. Okay, in that theory, which is ordinary classical mechanics, you can't ask what causes curvature. The question doesn't have any meaning there. First of all, we have to understand what we now will try to understand is that the curvature we are after is not curvature only of space, but of space and time together. Okay, and simultaneously we'll see what causes it. Both things we'll see now. So this didn't really involve any dynamics. Remember, I told you that this is a free particle. It could hardly involve dynamics. It's just a free constrained particle. Actually, everything I've done, I could have done from a geometric point of view without bringing in particles. Okay, but it's nice for a physicist to think of this problem as what would a particle do if it was left alone on a manifold, on a space. It would do something. We've calculated all the possible things it can do. It would propagate using the geodesic equation, and its Lagrangian would change if I change coordinates in a certain way, and that's the infinitesimal version. So that's all I've done. Okay, so now we'll bring in physics, real physics. And this real physics basically consists of two observations which follow from some very classic experiments. One of them is Newton's law of gravitation. And the other is Einstein's theory of special relativity. So let's first discuss Newton's law. Okay. So the key object in this is that there is a function phi, the gravitational potential, and such that the force acting on any particle is minus the gradient of phi. Okay, is actually minus, the mass of the particle times the gradient of phi. That's the statement. That's one part of the statement. The second part is what determines phi. Okay, phi clearly will be determined by some matter distribution which produces the gravitational field, and so phi is determined by using my older notation, del I phi is equal to 4 pi g Newton rho. These are both taken to depend on the three. This is all just statics, okay? And rho is the matter density, so it's mass per unit spatial volume. Okay, so these are the two ingredients. We start with the second one and say, okay, let me have a matter distribution such as the earth or something. I solve this equation and I find out the gravitational potential. I plug that in here and find the force acting on a particle. I integrate that to find the trajectory of the particle. That's what we want to find. Okay, I get everything from Kepler's laws onwards. Now, I mentioned this also last time, that this equation can be written mx double dot I. Here, don't worry about indices being up or down. I will not even bother to keep it straight here, maybe for once. This is the statement in coordinates of that equation. Okay, so in specific coordinates, grad is nothing but the three vector of partial derivatives, and force is mass times the acceleration. These two masses cancel out, so we get that the acceleration of the particle is determined entirely by the gravitational potential. Okay. Now, one thing you can certainly see from this law is that it doesn't have any chance of obeying the rules of special relativity, which says we can perform Lorentz transformations mixing up space and time. Okay? This doesn't have any chance of obeying that because space appears explicitly and time appears only in derivatives of this. Similarly, in this equation, you can see that it's a spatial derivative of this, and this is some mass density. Okay, it's not at all guaranteed that this equation is Lorentz invariant. In fact, it's not. Okay, so our goal will be to try and somehow fix that up using a little guesswork, but not too much, to somehow see whether we can get a Lorentz invariant equation and what it means. And one thing which will help us in our goal is to keep an analogy on this side. It's quite a beautiful analogy. It will tell you really why gravitation is different from everything else. So the analogy is with electrostatics. Okay, and is remarkable. I can write exactly the same words. So now there is a potential to confuse this phi with that phi. So here I am going to put G for gravitational. And here I am going to put E for electrostatic. Okay. Here the force is proportional to mass. Here the force is proportional to electric charge. Okay, that's a very important difference. And phi E is determined by the same equation. Okay. The constant on the right side here is called Newton's constant, G Newton, and it has a value experimentally determined.
So won't there be a minus in the case of electrostatics?
Sorry?
In case of
How will you define this?
Yeah. Yeah, there's a minus between them, but now I'm not sure which one should have the
It
minus.
depends on how you define the charge.
Okay.
standard convention is for positive charge.
All right.
Huh? No, force is minus that phi.
So then it will be minus.
In some convention, this is right.
Yeah, correct. Doesn't matter.
Okay. Now, this G Newton, its dimensions are easy to work out. It just has to convert from second derivative of, the first derivative on phi, has dimensions of acceleration. Okay. So then one more derivative, and this you know the dimensions, mass per unit volume, so whatever is left over have to be the dimensions of G Newton, and its value is 6.67 times 10 to the minus 11 meter cube per kilogram second square. And of course it's easy to see what determines it experimentally, because after all we can observe the gravitational potential by its effect on moving bodies, and we can measure the mass distribution. So whatever converts these two sides of the equation to each other is G Newton. Here I have given a fake name G electrostatic, though there isn't any such thing. All it really means, G electrostatic is better known to all of you under the name 1 over 4 pi epsilon naught. But whatever it is, it's a constant. And again, its dimensions are those which will convert a charge density into this side. Okay, so rho and rho, so write everything. Rho E is charge density. Okay, and this time the equation of motion for the particle written in coordinates will be mx double dot is minus q del I of phi electrostatic, and you see that m doesn't cancel from this equation. In fact, the equation depends only on q by m, or sometimes called E by m, the charge to mass ratio of the parts. Okay, that's why motion of a particle in an electrostatic field is a good way to determine its charge to mass ratio, but motion of a particle in a gravitational field is a very poor way to find out its mass, because the mass doesn't appear in this equation. Okay.
Sir,
Yes.
one thing I'm little confused is that in case of gravitational potential part, probably it has to be negative sign in the sense that
Where do you want the negative sign?
4 pi gn rho g.
Here.
Yeah. So in the sense that if rho is a positive matter density, then the gravitational field has to be it's a sink of the gravitational field, and that is reflected by the negative signs in the sense that first derivative gives you the gradient of the potential, that is the gravitational field, and then the divergence.
I would rather change the sign here if I have to change it, because I want this equation is just Poisson equation. It will determine some function. How that function affects motion of the object will be reflected in this equation. In this equation I am prepared to negotiate the sign, but I have a feeling my sign is correct there and wrong here.
No, in the other case, you have two charges, electrical.
No, all that I know. See,
Sir,
both in this equation, both are allowed to appear, right? Q can be positive or Q can be negative. But if Q is positive by the conventions that are used, then is this sign negative or positive? I think it should be positive. It's negative.
the standard convention is that Poisson equation for electrostatic will contain a minus sign.
Does contain.
Yeah.
Okay.
It's a standard
And this?
That's perfectly fine.
Poisson equation, this one.
Yeah, that will.
This equation contains the negative sign. Here, this will make you happy? Oh, then I'm happy. This suits me well. Okay, good. Fine. But of course, as you see, I could flip. Yeah, okay, that's fine. I think this is correct. Because finally, it's not totally a convention, because after all, like charges repel and like masses attract. So there is a sign difference. I didn't want to put it on that side. So you have given me a nice place to put it, and probably that's correct. Okay, good. Fine. So these are the two sets of equations, and now the point I want to make for you is that both of them fail to be relativistically invariant, but for slightly different reasons. Okay? And the solution to the problem is somewhat easier on this side than on this side. That's why I'm going to do this first, and maybe after that we'll stop and we'll do the gravitational case next time. So the equation which I am concerned about is this. It's not so hard to imagine fixing up this equation, because we just take the relativistic form momentum, put a dot on it, and put some del mu on this side, and we seem to have some equation. But it's very hard to fix up this equation to make it relativistic. So this is the equation I want to focus on. Not Lorentz invariant. Now what is Lorentz invariant? Lorentz invariance is a set of transformations which include rotations among spatial coordinates as well as something like rotations between space and time. Okay? Physically we understand that the rotations among spatial coordinates are ordinary rotations, but the ones between space and time are actually the boosts which give a velocity to one inertial frame with respect to another one. Okay? Now that mixing of space and time means that any equation which depends on a Laplacian del I has no hope of being Lorentz invariant. However, you know that if instead of del I, if I went to let me write it in full. If I went to this, then this combination on time independent quantities reduces to that. Okay, and it is Lorentz invariant because the Lorentz transformation acts as a certain orthogonal type of transformation on this, and when I sandwich eta in between, then I get back the same thing. That's Lorentz invariant. You want me to go through all that? Okay. So this one will take. This is also written in short as del mu, or sometimes as box. This is called the D'Alembert operator. So it's reasonable that we should make the replacement del I with box on the left side. That's the first step. Okay, are we home? Not quite. Now, the reason we are not home is a very physical one. What is rho? What is rho? E. So let's look at its units. It is charge upon volume, spatial volume. Okay. Is charge Lorentz invariant? Yes, it is. Is spatial volume Lorentz invariant? No, it's not. So how does it transform?
So
For volume, thank you. Good. So the idea is, let's put some time. This is just a dimensional kind of thing. Put a time on both sides of this equation. Now this guy is a 4 volume. The 4 volume is Lorentz invariant. This is Lorentz invariant. So we learn that this charge better be the time component of some 4 vector. So this is our first. So rho E must be the time component of a 4 vector. There is a, okay, so one thing we already learned when replacing this with box was that once we have, if we want to be relativistic, we can't do statics anymore. It can't be, we can't insist that we are doing everything statically, so it's not electrostatics. So actually at the end of the day, we have to somehow discover electrodynamics and not just electrostatics. Okay, and as you know, historically, that was the statement that relativity unified electricity with magnetism. Okay, luckily magnetism was already known, so people didn't have to say, oh, there's a hypothetical new force called magnetism which gets unified with electricity when we put in special relativity. But now we'll actually run through that argument and find that at the end there is magnetism. Okay, what will magnetism be? It will be the discovery that phi E is part of a 4 vector potential whose other 3 components are the vector potential which is responsible for magnetism. So just telling you where we are heading. So my point here is that everything will become time dependent, inevitably, but more than that, rho cannot be a scalar. We could have said, okay, let it be a scalar which depends on space and time. No, because its transformation properties are wrong because of what it physically is. It's a charge per unit spatial volume, and that's the only thing it can be. So it can't be a scalar, it must be the time component of a 4 vector. The conventional name for the 4 vector is J mu, it's called the current. And as a special case, in a particular frame, if you have a static situation, you can certainly arrange that J mu is rho 0, 0, 0. Okay? But you can't insist on that always being true in all frames. Okay? But if it is true in a particular frame, then of course the equation we are going to write has to reduce back to the equation in the box up there. Now if rho is extended to a 4 vector J, then of course on the left side there must also be a 4 vector. So that means that phi, this tells me that phi E must be the time component of a 4 vector. And this 4 vector is given the name A. I'm not writing that what they depend on because in a relativistic equation everything depends on space and time. Okay. So now we have an equation, and surprisingly we are not yet done, but it looks as if we are done. We have the equation box, which means this thing acting on E mu is equal to 4 pi G electric times J mu. Is this equation relativistically invariant? Very timid answers coming out. I'm not trying to trap you. Yes, it is relativistically invariant because that's what we are trying to do and we have succeeded. But we are not wrong for a subtle reason which I can show you immediately. There's a law, a physical law of conservation of current, which is otherwise known to you as the equation of continuity. So let me write it in different ways. Current conservation. This says that if I take the 4 divergence of a 4 current, I get 0. Okay. What is it in components? This is the same as d rho by dt plus plus the ordinary divergence of the ordinary free current equals 0, and in this language I think this is called equation of continuity. So that the charge density changes by the amount which is the divergence of the current, which is how much the current is taken away from there. Okay. Now let's try to apply that to this equation, and we find a paradox, because if we take the divergence of this on both sides, we find box of del mu a mu equals 0, because del mu of j mu is 0. Okay? Now if box of del mu a mu is 0, this is Laplace equation in free space with no source on the right side. The only regular solution is that del mu a mu equals 0. Okay? So, although we have learned that phi e is the time component of a 4 vector a mu, we have to accept that the 4 vector comes with a constraint called transversality, that del mu of it is always 0. So it's really not 4 independent components, it has one constraint. Okay, and you can in principle work with this system, this equation and this constraint. Please notice that both the equation and the constraint are Lorentz invariant. So as far as our goal of being Lorentz invariant, nothing is wrong. However, it's inconvenient to work with a constraint field, and also conceptually it has some problems when we go to the quantum theory. And these are two motivations to try and modify this equation in such a way that it won't have any constraint anymore. So our next goal, I'm sorry I've run out of blackboard, I have to go up. So let me write the equation again. Box a mu equals 4 pi. A clever way to modify this equation is that we are free to add terms on the left hand side which vanish by virtue of this constraint. Sorry?
Lorentz gauge.
This is not Lorentz gauge, it's a constraint on mu. It may be Lorentz gauge in a gauge theory, but there isn't any gauge theory. Please note that this equation doesn't have any gauge invariance. Okay, if I shift a mu by del mu lambda, the left side changes. So, you are getting ahead. We are trying to derive gauge theory and we haven't reached there yet. Okay, I know that you've learned gauge theory, but we are trying to derive why it has to be like that. Okay. And why it has to be like that is we know the equation of electrostatics. We were led to make it relativistic by this means. We realized that this is going to satisfy a constraint. Now we are trying to lift that constraint. Okay? And the clever way to lift that constraint is to realize that we can add terms on the left hand side which involve del mu of a mu. This you can always do because this is 0, so you are free to add 0 on the left hand side. But you can do it in a clever way such that del mu of the modified left hand side is identically 0. These words will be puzzling, but when I do it, you will see what I mean. So I want to add to box of a mu, I want to add minus del mu a mu. And I claim that this is the equation that I want. Is this the same equation? Is this along with del mu a mu equals 0? This pair of equations are the same as this pair of equations? Yes, you agree?
Yes.
Because I have taken this 0 being 0 and put it into this equation with an extra derivative on it. So this term is 0 because of the second equation. Okay. Now, however, I notice that this term can be rewritten as del mu of del mu a mu minus del mu a mu. Okay, but now we beautiful thing has happened. Now supposing I have this equation and I try to impose continuity or conservation of J mu. I put del mu on J mu, I get 0. What does that tell me about the left side? If I add to del mu on the left side, what do I get? Del mu on this whole thing. Identically 0. Identically. So now continuity doesn't put any condition on the left side. Okay. So this is what I meant. I wrote add some term involving del mu mu on the left side such that del mu of the new left side is identically 0. Okay. So this is some antisymmetric quantity which we'll call F mu nu. The equation is del mu F mu nu equals 4 pi J mu. And this equation now has all the properties we want. It's of course Lorentz invariant because all our manipulations after reaching that stage have been just to combine terms which are all Lorentz invariant. But more importantly, now the gauge field has no constraint on it. Instead, this has a new invariance. Delta A mu, or let's write it in full form, A mu goes to A mu plus del mu of a function lambda, arbitrary function lambda. As you see, if I plug that into this, then F mu is invariant by virtue of antisymmetry of derivatives. Okay, this is called gauge invariance. And the beauty of things is that after reaching this point of view, after reaching this equation, a person in the early 20th century would have stared at it for a while and said, that's funny. This doesn't only contain the equation I started with, but it also contains dE by dt plus curl of B equals J, which happens to be another Maxwell equation. That's the statement that you can check up for yourself. This includes the equation we started out with, which is del dot E equals rho roughly, that Maxwell equation, and we got the other one involving curl of B for free by imposing Lorentz invariance. Okay, but we learned on the way two things. One is that, of course, to impose Lorentz invariance, you can't make do with a scalar potential. It must be a vector, 4 vector. Okay, so the scalar must be part of a 4 vector. I mean, what we used to call a scalar potential, now we understand that it's part of a 4 vector. The second thing we learn is that if we don't want the field to satisfy any constraint, then we must re-manipulate this side such that the term on the left side is automatically conserved, that is del mu of it is 0. After that we can forget about the constraint del mu equals 0. But what we get instead is a new symmetric called gauge invariance. Okay. Now, exercise for you between now and Thursday, do all the same things with the Newton equation and derive general relativity. And if you don't do it by Thursday, then we'll do it in the class. Okay? Any questions?
I didn't get the exercise.
Well, I can tell you the exercise. Repeat whatever I did using electrostatics. Change your starting point from electrostatics to Newton's gravitation, theory of gravitation, and try to make it self-heuristic. Following all the steps I used. That's it. Yes.
Just repeat the last point.
Yes.
Gauge invariance.
Yes. So, between that equation of box mu and with a constraint and this one, the difference is it's the same equation except that we have lifted the constraint because this side satisfies del mu of it equals 0 identically because of antisymmetry of F mu. So we don't need the constraint anymore. Okay? But instead we get something for free. We get that there's a new symmetry in this equation, which is that I can vary A by an arbitrary amount proportional to del mu lambda, and this equation doesn't change. So the lesson is you can get a new invariance by when you make a theory relativistic, you get new degrees of freedom but also new invariance. That's the lesson.
You're basically using the
Gauge invariance thing was not there.
It was not there up there, right? Is it there up there? Can you see such an invariance up there? shift a mu by del mu lambda, that top equation is not invariant.
You're conserving a current and therefore you get symmetry. That's what you're doing.
Yes, of course, but it's not, I didn't do it in the, I didn't use Nuttall's theorem of field theory. It is, of course, finally what I'm doing is using Nuttall's theorem, that conserved current and symmetry are linked to each other. But I think the important lesson here is that you can either work with a constrained field or a gauge invariant system. That's what I want to display. Either the field has to satisfy a constraint or the system has to be gauge invariant. You can't get rid of the constraint without introducing gauge invariance.
And did we assume the charge doesn't vary from frame to frame?
Yes, we certainly did that. Well, do Lorentz transformations act on charge? Last I heard they didn't. Did Einstein tell you that when you travel in a rapidly moving train or a rocket ship, you measure different charge? No, it said mass changes, time changes, but it didn't say charge changes. No experimental evidence for that. Okay? Yeah.
Is this construction generic? Can you always remove a rank, let's say some rank P gauge field by a P plus 1 field tensor? A constrained rank P gauge field removed by a P plus 1 field tensor?
Possibly.
Or is something very specific happening in this construction?
Well, it will happen at least once more. And then it's enough because the only ranks we are interested in physics are 1 and 2.
In general, if you ask the question, purely geometric study, can you always eliminate this? A rank P gauge field by a P plus 1 field tensor?
Probably. The only people like string theorists would ask the question like that. It's a good question, and probably you can. Yeah. I think it has to be antisymmetric. The metric is unique in that it's not antisymmetric, it's a symmetric tensor. We don't have much experience of other symmetric tensors in any physical application. Except antisymmetric tensors, yeah, plenty. For those, it's the same procedure as true.